Dylan Tweed, a postdoc of Avishai Dekel, and I'm going to present my work with Daniel Severino simulation. So what we have is several series of simulations. All are simulation. Well, already we've been talking about them quite a few times. So we've got 3 generations of simulation. Generation 1 with 50 parsec resolution and 30 pairs of generation 2 and 3, which have all both the same resolution, 25 parsec. That's always pairs of simulation, meaning that generation 3 is the same initial condition as generation 2, but with a different feedback. What the focus of our work is, as you know, VDI, disk bulge evolution, blue and red nuggets, and inflow and outflows. So I'm going to tell you about my part in this different work. So first, the different galaxy samples. So that generation 1, we've been publishing with it already. So resolution, 50 parsec, thermal feedback, and generation 2 and 3. So I'm only showing part of the samples that those I have already analyzed. There is more than we have in the clusters that I'm going to analyze in the next few weeks. So these are generation 2, and that's the same simulation as generation 3 with the radiative feedback. So I can show you some mosaic. This is one of the generation 2 simulation, and that's a simulation that Chris Moody showed you earlier. This is the gas, and you see the galaxy evolving from redshift 2 to redshift 4 to redshift 1. And you see the same simulation with the radiative feedback. So you see globally we have a large X and stable clumps, but you see in the inner structure different in the shape, in the way the gas is distributed. Still, that's not really the topic of this talk. I'll move to the analysis I'm doing, which is uniquely based on stars. So simply speaking, I'm running a group finder on the stellar population. Since stars are tracer particle, I can run a merger tree. And from that merger tree, okay, from that merger tree, I can extract the clamp, separate the in situ clamp born through VDI from ex situ clamps, and pursue the analysis on the main galaxy and track the origin of the stellar population. So what is a merger tree? Merger tree looks like that, so I'm using the De Lucia-Blazo convention, meaning that this is the past, this is the present. Each symbol represents a galaxy in case of a circle, or clump when I use a square, and the color is just an indication of specific star formation rate. You see here the main galaxies, that the object we're interested in, but we keep the information of the secondary progenitor all around there, just distinguished between different types of mergers, major mergers, minor mergers, or mini-minor. Of course, you still have some ongoing mergers even at the last step that we can see as ex situ clumps at the end of the simulation. So back to the question of this talk. How can we follow the bulge? How is the bulge built? So we track the galaxy in time through the merger tree as just shown you. Now we need to extract the bulge. So how are we going to do that? Here's a picture of the galaxy. So that's a face-on view of the stellar population, and the same thing age-on. So what we're doing is a kinematic decomposition. We measure the angular momentum of any specific star projected against the spin axis of the galaxy and normalized by the maximum angular momentum it could get. So that's this number in the x-axis here. And then we simply do a simple cutoff at 0.7. That's a very classical method. And everything which is within this region is defined as part of the disk. So indeed, you see the disk face on here and a edge on here. About the rest, how to extract the bulge. What I'm using is I'm taking the spheroid here, or here if you like, and I'm taking the half mass radius of the spheroid. So I define this radius here, and everything below this radius is defined as a bulge. So that's what we have. As a little bonus, I separated the clumps from this frame and show where they lie in this diagram, and you can see the in situ clumps which have no galaxy progenitor lying in the disk. So it further demonstrates that they are formed in the disk through VDI, and the ex situ clump which lies in the stellar halo part of the galaxy. So since we can track the bulge, let's look at this mass evolution. So here is a stack of all generation 1 simulation, and since they all don't finish at redshift 1, I separate them into 3 subsamples. So the red subsample contains 27 galaxies, and I normalize the merged mass to the mass at redshift 2. So the line is simply the average, and the shaded region is the 68th percentile around the median. So what you see is the growth of the bulge. It seems that the growth against redshift becomes quicker in the end, but it becomes much more clear if we look at the second subsample, the subsample of the red, the one that actually reached redshift 1.5. So same story, throw normalized to the mass at redshift 1.5. And you see here that you seem to change the growth of the bulge with time. You can see that again in the smallest subsample of the 7 galaxies that reach redshift 1 here. And maybe to get a better estimate, we can superpose all the curve. Also, doesn't mean that the red subsample would actually look like that. It's just an estimate, just to collapse the whole figure. And we see that we would expect to have quite a slow growth until redshift 2.5, and then kind of a faster growth. I want to work a bit more, especially with generation 2, before making a very strong point of it. So we're back to the main question, is how are we going to build the bulge? So we track the bulge that I showed you, but now we want to understand what is the bulge origin, whether it's in situ or whether it's ex situ. So I have a merger tree, so I might as well use it. And I have tracers, so I'm using them as well within the merger tree. So I'm going to use individual stars and tag them, whether they are formed in situ or ex situ, to see what is the origin of the bulge. So we end up simply to the plot that Avishai showed you, is that the bulge at all redshifts, that's also a stack of all generation 1 galaxy. So it's a bit complicated, so let's focus on the red first. The red is all the stars which are born in ex situ. So all are created by different kind of mergers. And we see that accreted stars represent a very small fraction of the bulge. Only 20% at redshift 4, but at redshift 1, we reach more than 50%. The interesting part is really that the bulge is indeed formed in situ. So in situ is all which is blue and green. Green is actually what is due to disk migration. So green is stars born in the disk which fell into the bulge. So that's actually VDI-driven migration. As for the blue, it's a bit more tricky, because we know that stars that are born in the spheroid but we don't know where they come from. So the next question we will have to ask in the future is, where does the gas come from? Whether it's majors or whether it's VDI. So, of course, the main issue is that we are using IMR simulation, so we cannot trace the gas. So we'll have to find a way to associate the gas maybe with the stars, or to follow the gas info through wet measures to make a real conclusion about the origin of the gas in those bulges. So to summarize, we have a very large sample of simulation. I presented only results of generation 1 because I'm completing the work on generation 2 and 3. So so we'll have results with 30 pair of generation 2 and 3. This pipeline of analysis is used for several projects. One of the most interesting is, of course, the Blue-Red Nugget project led by Adi Zolotov. The remaining work that we can do using this pipeline is compare the effect of resolution using generation 1 against generation 2 and 3, and see the effect of feedback, especially on the bulge growth and the gas accretion, by comparing generation 2 and generation 3. So the remaining equation I have to solve is actually the origin of the gas to build the stellar bulge. Thank you.
Questions?
So the way you define sort of in situ accretion for the bulge, I assume that sort of wraps up anything that we might call a stellar halo as well.
What?
So if we think of a stellar halo as accreted,
Yeah.
would that automatically be part of your definition of the bulge? Because a stellar halo is presumably also accreted. It's also of no angular momentum. It ticks all
True.
the boxes. So could I think of the accreted component of your bulge as a stellar halo?
In fact, we see I separate through a radial cutoff, which is precise enough, well, a good approximation enough. But if I look at the stellar halo itself, what I define as the stellar halo itself, I don't see the same thing at all. I think that it's dominated by accreted material. So you might argue that maybe the accreted materials I find in my bulge might be part of the stellar halo. I don't know, because it's really straight at the center, so we need to find another argument to separate the halo from the bulge.
It might be better to cut in energy rather than in radius. At least that way you avoid things that are just passing through.
Good point. Yeah, indeed.
Other questions? Yep.
Can you go back to the plot where you have the different color bars showing the fraction of bulge?
Yeah.
I may have missed this, I don't know if you said it. Yeah. So when you say, so you take the fraction divided by the bulge, is that the bulge mass at each redshift, or is that the final bulge mass?
No, no, that's the bulge mass at each redshift.
Okay. So then do I take from this that, and maybe this is, again, the point you were trying to make, that in the beginning it's all in situ?
It's all in situ in the beginning.
In situ.
Yeah.
And so is it just that you still get in situ star formation, or does that get?
Yes, indeed. Doesn't show well here, and even in other plots doesn't so well. But still, you have always in situ formation. And if you compare even the age of the stars, you'll see that you have in situ formation at all times, but you have the subpopulation of ex situ star, which is much older. But in situ formation does occur at all times. If you compare to Near's results, where it's telling you that there is always a bulge clump, that's where these stars are born. you have a gas clump in the middle, and that's probably there that the star formation still continue inside the bulge.
Do you have enough dynamic range and mass to see trends in this plot with, you know?
You mean different galaxy mass? With this sample, no. With generation 2 and 3, I think we will. You can confirm that, Daniel? Yes.
Yes, for this simulation, they all have very similar
Yeah.
mass at the end, so you can really start.
Yeah.
For
Yeah.
for the new simulation, you have much broader.
Yes, that's part of the problem. We've got to think about not mixing the different realization.